Today I've got a problem from Oxford University's Maths Society, which is the invariance. This problem is all to do with isometries and isomorphisms or linear isomorphisms, which maybe you haven't seen before if you've not done much university maths before, and that's totally fine. I've just defined them here. So a linear map or a linear isomorphism is just a function which satisfies these two bullet points. So t of x plus y equals t of x plus t of y for every point x and y in R to the n, and t of alpha times x equals alpha times t of x for all alpha in the real numbers and all points x in R to the n. So t here in all three of these parts represents a linear isomorphism. Oh, I should probably also just define what isometry is. Isometry is just a distance preserving map. So if t is an isometry, it just means that the distance or the length of t of x is the same as the length of x for any point x in R to the n. Okay, so T is a linear isomorphism, and we've got three parts here where we kind of vary the conditions and ask, is T an isometry? So part one, suppose there exists x and y in R to the n such that x and y are distinct, and that the distance between T of x and T of y is the same as the distance between x and y. Need T be an isometry? Part two, suppose there exists some point C as such that for any point x, we have that the distance between T of C and T of x is the same as the distance between C and x. Need T be an isometry here? And finally, part three, suppose that for any 3 points x, y, and z, at least one of these three equations is true. The first equation says that T of x minus T of y in length is the same as x minus y in length. And the other 2 points are pretty similar, except with x and z and then y and z. Does T need to be an isometry here? Let's dive in with part one. This is incorrect. He does not need to be an isometry, and I'm just going to provide a simple counterexample here. Let's suppose we have the map T, which takes A, B, so we're working in R squared here. So it takes in the point A, B, and it spits out 2A, B, like so. It's pretty easy to check that this is indeed linear. We just need to show that, firstly, there are some points, X and Y, which are distinct, that have this property. So we can just say, let's look at 0, 1, and then 0, 2. And if I do t of both of those things, and then look at the difference between those, like so, well, what is t of 0, 1? Well, I just double the x coordinate, which is 2 times 0, which is 0, and the y coordinate remains the same, so 0, 1, and then same for 0, 2. And of course, this kind of very clearly satisfies that property there. However, T doesn't need to be an isometry. We can just choose an x here to be any number or any point in the plane which does not have x coordinate 0. So for example, if I look at T of 1, 2, for example, the length of that, well, what is T of 1, 2? Well, it's I double the x coordinate, so it's just 2, 2. And this is clearly not going to be the same thing as the distance of 1, 2. And so, yeah, it does not have to be an isometry here. Okay, cool. Let's look at the second part. So suppose now there exists some c in R to the n such that for any x, we have this equation here is true. It turns out that t does have to be an isometry. How can we prove this? Well, let's just fix y to be any number or any point in R to the n, I should say. And what we're going to do is just let x equal c minus y. So let x equals c minus y. And if we just sub it into this equation, we're going to get what we need. So if we look at the modulus of t of c minus t of x, if we just plug in what we've let x to be, this is going to be t of c minus t of c minus y. And now here's where we're going to use the linearity properties to kind of split this up as t of c minus t of y. And then this is just going to boil down to just, well, the magnitude of t of y. The t of c's will cancel, and you'll get just t of y there. Okay, cool. But we know that this thing here, according to the assumption, is equal to the distance between c and x, which is going to be c minus y. And again, if you simplify that, you get y. And so therefore, those two things are indeed the same. And here, y was an arbitrary point in R to the n. There was nothing special about it. So if it's true for an arbitrary point, it's true for all points in R to the n. And so t is an isometry. The final part here, we are assuming that at least one of these equations is true. Similarly to part two, we're going to fix a point w in R to the n. And what we're going to do is we're going to say let x equal w, y equals 0, and z equal minus w. Now, if we get that the first bullet point is the correct equation, well, what does this boil down to? Well, if x is w and y is 0, we're just going to get t of w minus t of 0 equals w minus 0. But of course, w minus 0 is just w. And a pretty easy to prove property about linear functions is that t of 0 is always 0. And so this just spits out that t of w equals w in length, which is ideally what we want for an isometry. But of course, there's no guarantee that it's the first bullet point that's correct. It could be the second one. Well, what happens here? Well, we get something quite similar. We're going to get t of w minus t of minus w equals w minus w. And this is going to be obviously 2w. And this here, if we use the linearity of t, this is also going to be 2t of w. And if you simplify this, you're again going to boil down to t of w equals w, like so. And if you use the third equation, you get something extremely similar as well. So regardless of which equation is true here, you're always going to end up with the magnitude of t of w equals the magnitude of w. And since w again was an arbitrary point here, it's true for all values w, and so therefore t is an isometry. It's kind of cool. I think this is an interesting problem, especially if you've just been introduced to isometries or linear functions and kind of are exploring their properties. It's a really good way to really assess your understanding of what these functions are and what these properties mean, as well as kind of seeing a nice common counterexample along the way. Thanks so much for watching. If you're new to the channel, please do give this video a like and subscribe if you haven't already. I'm close to 10,000 subscribers, and I guess something cool happens when I hits 10,000. I don't know. But let's get there first and we'll see what happens. Anyway, thanks so much for watching. I'll catch you in the next one. Have a great day.